Hello and welcome to Happy Maths Hour. It's all about reflections today, and we've got some activities that you can do. You see me making a complete fool of myself.
Oh no!
with reflections.
Yes.
And that, ladies and gentlemen, is reflections. So this is in Cosmo Caixa in Barcelona. I was doing bubbly maths, and this exhibition was there, all about mirrors and reflections. Did I use magic? Did I use special effects? Well, actually, yes. I guess I did use special effects because it's all mirrors, isn't it? I love that picture. I really love
Well,
that
I sat by that waterhole for hours with my husband and watched different animals come and go. And this is one of my, well, I love elephants. There you are. There's a reflection. And this show is all about reflections, different sorts of reflections. And he was just seeing Caroline with a mirror. What about this one, Caroline?
I can't tell you how much I love that picture. I've heard of Mirror Lake in Oregon, and I've seen pictures of Mirror Lake in Oregon, but it's definitely one of those places I'd love to go. But it's so smooth, you can barely tell the difference. You could turn that upside down practically, and it'd be like, okay, which way is the right way up?
It's brilliant, isn't it? It's just so tranquil. It's unlike the previous one where you saw there was ripples in the water hole, the water in there with the elephant. Now here's another one. What about that one? That's I walked along there with my husband. He took that picture 2 or 3 years ago, but imagine that 150 years ago when it was a busy canal taking lots of goods from a factory or from a farm up the canal or down the canal. Leeds and Liverpool are two big cities up in the north of England. And this is a small village through which the canal goes. Yes, I remember when I was a child, those big horses. Do you remember the big horses that used to pull the barges, Caroline?
I don't remember them from my childhood, but I have been on a pleasure cruise as an adult to experience it. And we were pulled by a horse. And the interesting thing was we had to go through a tunnel. And in the olden days, what they had to do was they would get they'd unhook the horse, who would then get taken, walked around to the other end of the tunnel. And the men would have to get on their backs on the roof of the barge, and they would use their feet to propel the barge through the tunnel.
Oh, wow. Well, I was born in 1940, and at that time, you know, some of those big horses still pulled ploughs in the fields, as well as other brother horses being used on the canals. There you are, Caroline. More of you and this mirror exhibition in Barcelona, and you've got mirrors behind mirrors behind mirrors. Yeah. So you see, it's a little like the Hall of Mirrors in Versailles, that effect. Although Caroline isn't in this beautiful sort of 1700, 1800 gown. Now, this is a young couple, but now you see mirrors in the round, and you can see reflections of the same people all the way around. That's interesting, isn't it? We call it a kaleidoscope effect. Here's Caroline again, 2 views of Caroline between the mirrors, and you can see multiple reflections of Caroline. So we're getting more than our money's worth. Lots and lots of Carolines. I think it's brilliant. She's going to show us some wonderful demonstrations of this. So Caroline's got a cardboard box and just some very cheap mirrors, and she's going to do some wonderful things with them.
I'm going to show you the effect, and then I'm going to show you how I did it.
Caroline, sweetie, I think it must have cost, that exhibition you were talking about in Spain, it would have cost thousands of euros to set it up.
Oh,
how much
absolutely.
How much does this cost you, Caroline?
two plastic mirrors, a box that I didn't pay for. It wouldn't be as clear, but you could actually do this with silver foil on cardboard.
Oh, I tried it with aluminium foil, kitchen foil, and it doesn't work terribly well, but it does work. And so you can actually do it very cheaply in your school, even if you haven't got much to spend. And probably somebody in your household has got one of these vanity mirrors. That's what we call them anyway.
This is the real Father Christmas right here, and you can see he's looking at the mirror behind. But if you look behind him, you can see the back of his head, and then behind that, if you can just about see that, you can see his eyes. So he's facing himself for the first one, and then again, and then again, and then again and again. If you seeing it in person is a lot easier, and it actually goes on forever, just limited by the quality of the mirrors.
You can see lots of mirrors, Caroline, but you've only got 2 mirrors in this display, haven't you?
Now I'm going to show you the setup. So there's the setup. We've got one mirror here. I've got my little Santa Claus. It could be anything. I've got another mirror here, and I've just used a cardboard box. Just test with lots of different things, and all you need is a cardboard box and 2 mirrors. We've got these shapes. Now they're actually the same area and slightly different front and back, because the blue's on top left corner there and the blue's on right top corner there. But if you look at the reflection, you can look at the reflection in different, you've got these different ones. They're 2 different patterns. You can see all the different possibilities depending whether it's 180 degrees or going around that way as well. And then you've also got, of course you've got not just reflections, but you've got rotations as well. So that was
what Caroline has very cleverly done there is she has, with one mirror, she's able to demonstrate reflections, but she's also prepared the rectangles so that if she turns it over, you can see the reflection as well.
Yeah.
And you can see in the mirror that that's what it is. And then she can do it by actually physically rotating it as well. So you can see there's one arrangement of these squares and rectangles, but what we were looking at is reflections and rotations of that same pattern. So that's lovely, Caroline. Well, a very nice demonstration. Now we're doing this sort of on the cheap because we haven't got any money anyway, but the main thing is that you can do it at home with your children if you want to, or if you're a teacher, you can do this in school, and it costs you very little to get the mirrors, and then just some cardboard boxes help you. Well, Caroline, what about your cubes? You did your cubes.
I've got my itty little cube here. This is my trusty little cube. It's 1 centimeter cube. It's 1 centimeter on every edge. And what's going to happen if I put it here? What do you think is going to happen? Let's see. I'm going to push it closer and see it going in a bit closer.
The good thing about this is that she can take her hand away and we can see it.
Yes.
We've got 4 cubes now. 4 for the price of 1.
So the dimensions are 1 by 2 by 2. So I've got 1 high, and it's 2 long and 2 wide. Now, how could we make that into an actual cube that's either 1 by 1 by 1? Well, that is 1 by 1 by 1. What's the next thing that we can make a cube? It would be a 2 by 2 by 2. Well, thought about that, and I thought, well, what happens if I make a 2 by 1 by 1? Then what would happen? What if I put it that way? Well, that's not quite.
Well, that's a cuboid, isn't it?
It's a cuboid, and it's 1 by 2 by 4.
Yes.
So what if I do that?
Caroline, you've got another 1 cube now. Isn't that clever? 2 by 2 by 2.
Hooray. And then this is something we do with a different workshop. I've got I call it 100 cube. Every face is 100 square centimeters. Now let's see if we can see this. This is a challenge. So you're going to have to visualize it a little bit.
Well, we can see most of it, Caroline. And there are 1,000 of the little ones in the big cube. That means the volume of the bigger cube is 1,000 cubic centimeters. And in the mirrors, we can see 4 of them.
Yes, but is it a cube?
No. Is it a cube? No, it's 20 by 20 by 10, if you like.
Yeah. And so what would we have to do to make it a cube? I'll leave that with you. And now we've got paper with a detailed design, and what I've got is a mirror in my hand.
Caroline, now it's looking kaleidoscopic.
Yeah, you mentioned the kaleidoscope earlier. Let's see, what have we got? We've got 1, 2, well, we've kind of got 4 squares again, haven't we? And
This is amazing.
Now,
yes, 4 squares. Now, Caroline's changing the angle between the mirrors, and look what you're seeing. You're seeing more copies of the same pattern now, and like the couple we saw in the museum, and we saw reflections of those, multiple reflections, but all around them, not just in a long line. And as Caroline now, she has got reflections of that. Is that?
There's 6 there.
6 reflections. And so she's got her angle of 60 degrees, which means she's got 6 reflections. And now, well, you could get 8 reflections, Caroline. It's 45 for 8.
That is.
Yes, that looks it. Yes. So she's got 8 reflections now, and that's with her mirror at 45 degrees. 8 times 45 is 360.
Yes. And now.
And she's getting more and more. How many have you got now, Caroline? Oh.
It should have, in theory, this is 22.5-ish.
So that should be 16.
My mirror's a little bit bent. I don't have, they're not, the join isn't exact, but you can see those straight lines. It's not perfect, but you get the idea. And a child can be looking through here and really, really see, and take pictures with a camera. And actually it looks better with the camera than it does looking at it direct. You are getting a better view with the camera than I am getting by looking directly at it.
It's beautiful. It's a great demonstration. But how exciting this would be for children at home playing around, and all you need is some simple props, a couple of mirrors, and these, you know, very, very simple ways of sort of moving them at different angles. And the children will learn so much about angles and about reflections. And in the school maths, we do learn about reflections and rotations and translations, which we'll talk about a bit more. And then this comes into real life in applications in crystallography and, well, in art too. And it's such an important topic in a lot of applications of mathematics, and it's something which makes the maths come alive for children if they do it themselves. So either at home or in groups in the classroom. It doesn't cost much to set this up. It doesn't take a lot of time either, but in groups of children could work on it.
I just wanted to say that I used the boxes because we had to have straight lines. We needed 90 degrees, and that occurred to me to use the boxes to get that, so without having to construct it. Tony, you've got more exciting things for us.
Indeed, yes. You've just done this with the demonstration with your 2 mirrors at an angle, and now you can see this demonstration in the museum with this couple here, the girl with the backpack, and reflections of them. You can see the same effects there. And we'll look at the theory of this in a minute. But what you see very clearly there is a hexagon, a 6-sided shape around this couple, and there's mirrors at 60 degrees, and it's producing this effect that is really fascinating.
It was a hexagonal prism, so you were going through a tunnel that was hexagonal in shape, and let me tell you, I had quite a lot of trepidation about entering it because it felt as though you were going to step into space. You didn't you could see in every direction going off to infinity, and it was like, if I step on this floor, I'm going to fall through it. It was really quite amazing. Sense of space.
Yes, now I'm very intrigued. I'm absolutely intrigued by that, because I was thinking the angle was 60, and now I'll have to think again, because your tunnel, it seems to me, if it was a hexagon, then the angles would be 120. Interesting, that, isn't it?
It was really quite bizarre. Very
That's your
fascinating.
hexagon. Here we go, because we're going to look into the theory a little bit now. And the question that we're asking is, why do reflections in two parallel mirrors combine to give a translation? Now, Caroline showed this with Father Christmas. And here you see a girl in a similar display to the one that you saw Caroline in. The girl you see who's taking photos there seems to be in a lift. And if you look, you should be able to see that 3 walls of the lift are mirrors. And the effect you see of repeated images of the girl, that is because she's between 2 parallel mirrors. And the back of the lift gives us another image, but not including the girl. And as you see, alternate reflections, she's facing you, and not everyone, but only every other one is she facing you. And in the others, she has got her shoulder sort of half turned away from you. And when we talk about 2 reflections making a translation, what we mean is that a translation just moves something along without turning it. So if you look at the picture of that young woman facing you, and then you just imagine her being pushed back but not turning at all, the 2 reflections give you a translation. If you look at the blue flag, right, and it reflects in mirror 1 to B2, the first reflection is in mirror 1. And then if you reflect B2 in mirror 2, can you see that B2 and B3 are reflections of each other? And B1 it moves by a translation to B3. But that's 2 reflections. And so this is a little bit of an illustration. We put these up to challenge people to think. And if you go to the Aiming High website and go to Mirror Mirror, there's a lot more about these ideas. And the reason it says activity for all there is we believe that quite young children can start finding out and seeing and getting excited by mathematics without making it complicated for them. So children can describe and explain what they see in that mirror, even if they're 5 or 6 years old, or even younger. And you don't have to complicate it with the maths that's on the left. And we'll come back to the answer to that question in a few minutes. But what the challenge is there is to try it out for yourself. And that's just exactly what you were doing, wasn't it, Caroline? Trying it out for yourself.
And you can use a teddy bear or something to be the woman in the mirror. And her positioning is so perfect, though, isn't it, Tony?
Yes.
It's really so easy to see that her reflection alternates.
Yes.
And she's at an angle of 45 degrees, and then the reflection is 90 degrees to herself. If you look up closely at this, you can see it goes on and on and on and on forever. So it's a lot clearer photo than the one with the hexagons, because the hexagons, there was images everywhere. Whereas here, there's just one long line of images. Yes, and this brings to mind this this children's story, Mirror, Mirror on the Wall, who is the fairest of them all? There's a link on this resource on Aiming High to a song which is called Mirror, Mirror on the Wall. It's jazz, and I like it, actually, so I put the link on it. She's moved without turning, translated
but it's two reflections that give the translation, and that picture shows it very clearly. And the no smoking sign is reflected too, again and again. This is famous. This is hundreds of years old. Louis XIV, Hall of Mirrors, which he had built in Versailles. And you can see one picture on the left, which just shows the hall itself. And now just think about it. This picture shows a group of people in the far distance at the other end of the hall. And the person taking the photo is in the real group, taking the photo, and right at the other end, there's a reflection of the group, okay, far away along the hall. You can see it's just one hall, and look at the ceiling, you'll see there the design on the ceiling.
There's 3 lamps. So if you look on the left, you see 3 lamps, and there's only 3 lamps.
And on the right, there's reflections, as you saw Father Christmas reflected, and as you just saw the girl reflected, there's multiple reflections backwards and forwards, because now we've got 2 parallel mirrors here. And as you see from the lights, the ceilings, look at it, it's many, many, many receding into the distance. So
it's going on forever.
Yeah,
but it isn't.
That had people spellbound, because it was so mysterious and miraculous to them that you could get these wonderful reflections. They could see themselves again and again and again in all their finery at the court of King Louis. Now here we've got different patterns, and they are deceptive, because on the one on the left, it looks as if you've got a rose, and in the one in the mirror, it looks as if you've got some sort of flower with 6 petals, but they're not. They're just formed with 2 mirrors, as Caroline showed you, and the difference between these 3 patterns is the angle between the mirrors. And so you've got lots of symmetry here, and this time it's not reflection, it's not symmetry by reflection, it's symmetry by rotation. On the one in the middle, there are 2 mirrors at 60 degrees. And because there are 60 times 6 is 360, and you've got multiple reflections, but they're not repeating themselves in parallel mirrors so that they're going and receding into the distance infinitely far away. They're repeats round and round and round. And we talked about cycles before when we were doing Pathway to the Stars, like Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and we're back to Monday. And in 7 days' time, we'll be doing another of these shows. But this is a cycle of 6, is a pattern which repeats itself round and round, not every 7 days, but every 6. And here you get your sort of blue and purple flower with, oh, it's got some orange and green. It's a 6-fold symmetry, and some people say rotational symmetry. Some people say the order of rotation is 6.
And it's the 2 mirrors, and that's just make it 60-degree angle. And I secured one to a box, and then just moved the other one had a guide on the floor, and just find some really nice cloth and have a go.
Yes, it's no end to the different designs you can get with this very simple experiment. Now on the left, the rose there has got 9-fold symmetry. So if you divide 9 into 360, you get 40 degrees. So to get that pattern, you put your 2 mirrors at 40 degrees, and there you'll see a pattern which appears to have 9 petals and has got rotational symmetry. 9-fold rotational symmetry or rotational symmetry of order 9. Now you have to concentrate and count all the way around the one on the right, but this isn't like 12 hours on the clock or 12 months of the year cycle like that. This is a cycle here of 16. You'll see the same pattern repeated 16 times. And I've just realized, you know, Caroline, it looks like your Father Christmas 16 times.
Oh, it does, doesn't it? Oh, yes. How lovely.
That wasn't deliberate. I just saw it this minute.
And that's about that angle between your mirrors ish. You use a protractor.
Yes.
We just moved the mirror until we saw the 16 images, didn't we? And it wasn't perfect, so we're doing it by hand.
But you can see the right angles there, can't you? And you can see the right angles, 90 degrees, divided into 4, making a 22.5 degrees. So you've got your 4 Father Christmases in each quarter, which gives you 16 Father Christmases altogether.
4 Father Christmases per quadrant.
Yes, they are. So you've got 3 good illustrations there of this kaleidoscope pattern. We should be talking about David Brewster now. He lived in the 18th century. He was born in 1781 and he lived to 1868. So he obviously did a lot of work with mirrors, just like Caroline did. And maybe he started off experimenting in a similar way with just a couple of mirrors to see what effects. But of course, there was quite a lot of research going on into making better telescopes and better microscopes. And so it was very important research. It wasn't just playing and making patterns. And David Brewster was an inventor as well as being a very serious scholar, academic. And he wrote about his experiments. He did work in optics. He studied the polarization of light, which has quite a lot of important applications. He studied crystals, and I don't know anything about these sciences, not much at all, just a little bit from school physics. But crystals are very important because this is the stuff that matter is made of, and the way crystals fit together depends on the symmetries that we've just been talking about. We've just been thinking about symmetries, haven't we, in these patterns, and we've been looking at reflection as and mirror lines as lines of symmetry, and we've been looking at rotation, where we have got rotational symmetry with the pattern repeating itself. We saw 9-fold, we saw 6-fold, we saw 16-fold symmetry there. And the way things fit together, you've only got certain angles that you can make into a packing, so you can pack these crystals or shapes together, like in tiling a wall. What shapes can you tile a wall with? So there's decorative or artistic applications, but there's also serious applications in chemistry and physics.
Did you know they use bubble foam they still don't know the optimum shape for packing in foam, the foam industry that makes foam for beds and furniture. And they're investing still, and I think there's a prize for the person that gets the ideal shape. And it's based on, at the moment, the one they found is based on pentagonal and hexagonal tunnels, much like the fullerene. But it's actual tunnels. You've got this tunnel of pentagonal shapes going through, and then around it you've got these hexagonal shapes and interspersed with other pentagonal shapes. But they don't think that's the best one they found so far, but they don't think it's the absolute optimum one. They're still looking.
That's really interesting, Caroline. Well, my husband did some research with a man called Ken Stevenson, a mathematician in Tennessee. And we went to a conference with medical doctors, people in IT, and mathematicians. And it was fascinating because what they were studying was the brain. Now, would you believe it? You've got circle packing. So you were talking about bubble packing. This was about circle packing because the brain is actually crinkly. I mean, the surface of the brain is where a lot of important things happen which enable us to do all we can do as human beings. And it's a very crinkly surface, and it's very hard to pinpoint. You can't sort of use a grid like a graph in either 2D or 3D to say that's where that point is, because the surface of the brain is sort of going into little cracks and crevices, and get a piece of, I don't know, we were talking about silver foil, and crinkle it up. And then, so how would you map it? How would you refer to where you were talking about in the brain if you'd found a spot that was actually critical for some reason or other, as a doctor, as a neurosurgeon or a neurologist? And so they'd called in the mathematicians who were doing, would you believe it, circle packing. But if you make some of those circles really small, and I don't know, they understand the maths and do all that packing, then you've got the IT people there who do it on a computer. Well, that's what they were trying to. I don't know whether it led to success. Anyway, going back to Brewster, he was working on photoelasticity, and I don't know what that was, and that led to the modern science of optical mineralogy. He's called the father of modern experimental optics, and one of the things he invented was this toy called a kaleidoscope. And this, now in Victorian England, was a very popular toy. And they named it because scholars in those days were often scholars of the classics, not mathematics, and they liked to give Greek names to new inventions. So they used the word kalos, which means beautiful. And I think you'll agree these patterns were really beautiful. Then they used this middle word, eidos, which is that which is seen, a form or a shape. Finally, the word scopio, and I think that's occurred in other English words, the scope of something, and it means something like to look at or to examine. And of course, in telescope, you've got the same word, haven't you? Because you use a telescope to look at the stars. So that's where you're using scope in a similar way. And so altogether, those Greek words making one word, which comes to mean something like for the observation of beautiful forms. And there's a picture of a toy kaleidoscope there. And you can see that the cylinder at the near end, you can rotate. You can shake it, and it's got coloured little bauble bits inside, different colours.
Way somehow get yourself a kaleidoscope.
It's a cheap little toy, and very little tiny children. It's fun because every time they pick it up and look at it, they can make a different pattern, and then they perhaps can draw the patterns that they've seen. And with a bigger, you can do the sort of experiment with the box and a couple of mirrors like Caroline did. And you can then start to make designs in art. There's lots of fun to be had there. And then you can get a little more advanced and think about what are these angles actually, and why does this happen this way? And we're going to finish off with the prisms.
The challenge to you is to create this, make these shapes and put them, make any shape you like and put them on a mirror and see what happens, and think what shape they're going to be, and then test them. How about that, Tony?
Absolutely. Or take some photographs of reflections in water.
Everybody say we love that so much we can't stop. Take photographs, great idea. And take photographs of the reflections that you create yourselves on a mirror.
Goodbye, everybody. See you next week.
Bye-bye.
For greater understanding and enjoyment of mathematics, the Maths Toys YouTube channel is brought to you by AIMSEC and the Aiming High website. In the description, you will find a link to our home learning guide for ages 4 to 18 and a teacher resource pack. If you find this video useful, there is a GoFundMe link in the description to donate to and support AIMSEC. The money goes to bursaries for professional development for teachers in disadvantaged communities around the world. Subscribe, comment and ding the notification bell to make sure you